Okay, we can start the class now. And Amy, you have a question.
I was wondering, you had a test scheduled for next Wednesday, the 20th.
Oh, yeah.
Is it going to be on?
No, it's not going to be on next Wednesday. That is basically the system directly imports what the schedule from last year. So we can depend. So my point is the test not going to be Wednesday, but will be probably very soon because we're going to finish all the teaching of the lectures actually today for this chapter. So after we have done this chapter, it will be finished. No more new lectures on chapter 7. Today we're going to discuss about the distribution, about probability of the polymer chain. Then we're going to also talk a little bit about the real polymer chain, how these polymer chain would behave in solution. So those two topics we're going to cover. Then I will assign a short homeworks that covers radius, gyrations, rigidity, and the real chain stuff. So that will give you guys another week to finish. So then we can talk about the exam. I tentatively thinking about September 28th. So that will be 2 weeks from now. Jamie looks like very good, right? You like the date? Okay. Let's do 28th because I heard you guys have first a chemistry exam coming up, so we can do 28th. Okay, that sounds good, everybody. Tentatively, and I always like to have set up a lecture before the exam to answer any questions, go through homework, so that the Tuesday. No, is it going to be Tuesday? Yeah, the Tuesday before the exam, I'm going to carve out one lecture for everybody to answer any questions. And we can continue to do some teaching next week because we can start solutions, teach you a little bit. Okay? That's going to be the plan. Looks like we are missing someone today. It's not so crowded. So, yeah, if you guys know, then maybe send them a quick message, let them know. Otherwise, we can start. So, all right. Here is Jonathan. Okay. As we speak, we have one more student. Great. So let's begin today's class. As I mentioned, this is going to be the last lecture of polymer conformation. I mean, if you guys look back, we talked everything about polymer conformation from the size of polymer coil, the rigidity of the polymer, and we also talked about different models and how to measure them. Particularly last lecture, we talked about the concept of radius gyration. We discussed the relationship, what is end-to-end distance and radius of gyration, how we can kind of indirectly measure the RG to get the end-to-end distance, right? So hopefully by now, everybody should be very comfortable to say if I want to measure the size of my molecular, I have some idea how to measure it and how that's going to be related to my the total conformation of my molecular chain, right? We talked about different models, and we know how molecular weight will influence different end-to-end distance, RG. I'll re-emphasize a little bit at the end of today's lecture how they are linked. And for today's lecture, I'm going to cover two topics. One is distribution of end-to-end distance. Okay, this would be the one topic. The topic two we're going to cover is, let's also talk a little bit about real chain. So how does the real chain differs versus what we talked about is idealized chain. Okay, so we're going to cover those two topics in the next 40 minutes or so. So let's start with the first one. Let me project the screen. So, all right, slideshow. Why do we want to talk a little bit about distribution? So if you recall that throughout my discussion, when we talked about end-to-end distance, we we use our EE sign. End-to-end distribution. We always discuss of end-to-end distribution square, and we discuss about average, right? So we always talk about what is the average representation of the polymer chain. So one of the important consequences of this average is give you representation of the molecular, but didn't give you capture of individual property. To give you example, we know that we can use the difference between, let's use United States GDP average per capita. It's probably 40,000, right? Come on in, Dasha. And compared to, let's use in India, for example. India is a little bit less developed, so average GDP per capita will be lower, but doesn't represent how does each individual, right? Average only talks about ensemble. So you can have really rich person in US, you can have really poor person. So you can easily find someone really rich in India has much better quality of life than average American. So this lecture we're going to talk about distribution. So how does the individual chain distribute? So if you imagine we have a chain look like this, if we kind of in solution, it's not stable. I should not say stable. I should say it's not frozen. The chain will have change. It will have change in conformation, so it will diffuse, it might change shape. So at a given time, the end-to distance fluctuates, if that makes sense. So think about my hand is two ends of chain. So it's throughout my lecture, I'm gonna do all kind of hand gestures. So the distance distributes, right? At a given moment, I can be shorter, it can be longer. So we want to understand what this distribution looks like for chain and what would be end-to-end distance. So for a long polymer chain, the end-to-end distance at a given moment, it can be short. So that's what we want to calculate. What is the probability of distribution? That's probably the better way to describe what it is at a given moment you have a chance. So everybody learned about probability? Do we need a quick refresh? Amy says yes, let's do that for Amy. So wherever you start a sports game, what do you guys do first? Let's say soccer. Everybody line up. Then what next? The referee is going to call out the captain of each team, says it's going to be head or tail. Then he flip a coin. If you guess right, you get start the ball, right? So if you think about that's the case, if we have a one coin that is going to be flip head or 0.5% of tail, so we have a chance of 50-50, right, in this case. So that's where we talk about probability. If we flip twice, it has 1/3 time of two heads, 1/4, sorry. Two heads in a row. That makes sense. You flip once, it will be 50%. You do it again, it will be another 50%. And you would have one, and the other is heads, then followed by a tail. Equally, you have a tail plus a head. Then you have another 1/4 of chances, two tails. So that's what we mean probability. So probability comes from what the chance of one type of motion in terms of total probability. So the chance of every possibility add up should be 100%. Okay. So it's a little bit tedious to discuss about the probability of distribution. So we're just going to talk about conclusion. So here we showed what's the probability, P. And probability of distribution of chain N depends on two parameters. And everybody should know what is N is number of bonds. and r is the distance to the center of one chain end. So in this case, we're going to fix one chain end at a coordination of 0, 0, 0. Then let the chain do its thing, and we can see what is vector from start to end. R should be the end-to-end vector. So the distribution of this end-to-end distance depends on this particular equation. So let me walk you through what this equation is. Yeah, Joseph, question?
Is that R the same as REE, or that's just the distance from an end to the center?
That's basically the REE in this, because we fix one polymer chain at the origin. So R is basically REE, right?
Okay.
It's one end to the other.
Okay. Thank you.
It's not the mass center in this case. It's basically one end is origin of the polymer chain.
Got it. Okay.
Sure. So you got 3 divided by 2 pi times mb squared, and everybody should know this is the end-to-end distance square. And if we know a polymer's molecular weight, this basically is a constant. And we call it a normalization factor, because this basically we add here so that all the probability when it's add up will equal to 1 or 100%. If you don't have this term, your probability when it's add up, it's not going to be 100%. It will be bigger. So this is a normalization. We put it here. And you know, it only depends on n. It doesn't depend on the r. Okay, so this is where the fun part. You can think about probability is right now we have ink. So is a constant times exponent minus 3r square divided 2mb squared. Because we talked about P is dependence on the R and N. So if you look at when the R goes up, what's going to happen? It's an exponent term. It's a E. Power depends on R squared. These are constant, right? So it's effectively, I can imagine the P will be proportional to exponent times R squared. So that means your probability will go down very quickly with the distance increase. And that kind of makes sense. We did one example, showed you guys what is random walk. We throw a coin, we go back and forth. We understand that your chance of ending up where you start off is high. Your chance of going all the way out is decays with distance to the center. So if I plot this probability, it depends on the R, it will show up this. Probability will highest at R equal to 0. It decays quickly to infinity small number with the distance further away. So you can imagine, so if my chain has a million different motions, the chance of finding the other end closer to 0 is reasonably good. It's highest. Okay, does that make sense? Any question? Okay, so now I'm gonna say something really confusing. So Amy, you have a question first.
Yeah, why you have 2 different graphs there of probability and radius. What is the other one?
I missed your question. Yeah.
So on your slides, you have 2 graphs.
Oh, I haven't get to that yet.
Oh.
Yeah, I haven't to get that yet. So I'll just speak to you just a second. So the end-to-end distribution, everybody understand, makes sense. But now the next question is, what is the chance you find the chain end at a given R? What is the chance? So these are different things. I will slow down. One is distribution of a chain end. The other is what the chance to find a distribution at a certain distance away from. So the difference is as such that in order to find the same end distribution at a given distance R, we need to consider all the possibility of distance ended up in this H. So which means when you have chain end is small, the chances of finding it to be the small need to fit into this shell of a sphere. Because it's all satisfy the distance of h. Does that make sense? So your chain can be here, 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 here. The end-to-end distance is always h. That's the same. If we need to find a larger end-to-end distance, then I will draw a larger sphere. You will see the chances of finding an end-to-end distance at a given fixed value is also proportional to the distance, right? The further the distance away, you have more surface area. Because the surface we talked about is dependent on 4 pi h squared. In this sense, h will be the distance, right? So actually the opportunity to find the end-to-end distance at a given distance should be written 4 pi h squared times the probability. This we need to add this correction factor because the chance of finding a certain distance depends on the surface area of the distance. Does that make sense? So if you have a distance is 0, it almost has no surface. If you want a certain distance to be half of h, you will see if I draw an imaginary circle is half of the distance there, the surface area will be 4 pi times h squared. It will be much smaller than this red shaded area. Despite that, your end is probable there, but you're not going to find as much because the surface area of falling into that distance is smaller. So now if we plot 4 times h squared times p, this will be the probability, and distance to the center, or you will see a probability now show not just a linear decay, but you start to see a maximum. And then decay. So in other words, the probability of finding the chain end right at the center is smaller than it's having a distance right at this peak. And it will be going down again. Okay? This might be a little bit counterintuitive, but let me demonstrate. So this is again, at a given moment, your chain can take any conformation. So even at the fixed n and b, you can adopt this conformation. There's no problem. It's just not stable, and next moment it might relax back. So that's why we talk about this probability. On average, the distance will be mb squared. So if my chain can adopt 1,000,000 different conformations, if you take those 1,000,000, add them together, divide by 1,000,000, take an average, this will be an mb squared. But at any given moment, you have very little chance to find the chain is almost touching each other, where end-to-end distance equal to 0. You have a high probability find it at mb squared, which is what is supposed to be average, and the probability find it at higher distance will be lower. Okay, this is basically what it says. Any question for this part regarding distribution? So this gives you some realistic image of what the chain, a single chain, would look like. Or in a, just so I'll get what just think. Or in a solution, well, it's dilute, but there might be, let's say, you dissolve 1 mole of molecule in the solution. 1 mole is 10 to the power of 23. There's billions of them. You can zoom in to look at each individual. Some of them has larger end-to-end distance, some of them smaller. It will follow this distribution, okay? And then Joseph, your question.
So is that maximum on that graph right where nb squared would be?
I believe so.
Okay.
I believe so. We have a homework. We're going to ask everybody to calculate this. So, any other question about distribution? If not, then let's see. Oh, we're now going to talk a little bit about real polymer chain. So, what is the real polymer chain and what is not real polymer chain. So we're gonna now talk something really interesting because real polymer chain has most of the impact. It's something you can touch. And I like to use the example of I'm gonna dissolve a toluene, dissolve a polystyrene toluene because it's a good solvent for a good polymer. So in idealize the chain, we don't see solvent. Everything we talked about is just a chain distributed in vacuum, and the polymer can fold onto itself. And we know Rg. Now I'm going to use a sign that everybody need to watch carefully. We know Rg squared will be equal to Mb squared divided by 6 average, right? This we just talked about in last class. So everybody has heard about what is proportional means. Proportional means if Rg if I write this, that means Rg is proportional to n power of 0.5. That means when n doubles, Rg increase by a factor of root square 2. So that means proportional. It turns out it's actually a great way to understand how polymer size depends on your scaling. Because this is a scaling factor. Or we can write generally, Rg will depend on molecular weight, power. This is dp and molecular weight is the same thing, power of V. This is scaling exponent, okay? So in the case of ideal chain, all three models we discussed, freely joined chain, freely rotation chain, hinder rotation chain, actually all relies on this relationship, no matter what it is, because when molecular weight doubles, Rg will increase by a factor of root 2. It's universal for three models. And why? I'll show you. We learn about this particular relationship. End-to-end distance will be C infinity NL squared. Right? No question for this. This is written in textbook. So when we increase n, your RE will increase by a half. Does that make sense? RE has square, so we can also rewrite a little bit. RE equals to C infinity n times L.
What is the little like V over triangle in the?
Oh, it's just exponent. So I just emphasize that triangle. You don't need to write the triangle.
Okay.
So n exponent of V with V exponent.
And
Okay.
V is density or? Sorry,
No,
viscosity?
V is just an exponent constant. It doesn't mean anything. It's a constant. So I'll get to you really quick. So when V equals to half, that's basically all the idealized the chain is. Because when molecular weight need to quadruple to get end-to-end distance double. So we can say this has a scaling relationship of Rg depends on n power of 0.5. Make sense? Or you need a little bit more?
I'm wondering why you made it into a variable rather than just saying 1/2 like you did before. Like, why did you generalize it?
Oh, good questions. We're going to talk about a few other cases. And we will talk about idealized chain, then we're going to talk about real chain. Then we will talk about raw-like structure. They will depend on different V. And we will discuss how the different scales with, okay? And Sarah.
Is about the word proportional, the radius of gyration proportional to n with the exponent of 1/3?
1/2.
1/2?
Yeah,
Okay.
0. I'll try to write it bigger. I know
Yeah.
the ink is, I'll try to also use a black ink. This one, this works. Okay, so any more questions? Because the exponent, how it depends is really matters. So in good solvent, I'll first talk about, in good solvent, it's already kind of shown here. So the Gaussian chain is approximately 3D random walk. And, you know, we already discussed the 4 or 5 lecture of it. So for large chain, it's quite a different because your chain, when it's through a random walk, it just can't walk on itself. It's just horrible, horrible when 2 chains collapse on each other. Atomically, it's exclusive, right? And everybody probably haven't discussed in depth, but in physics, we know there's short-range forces when you have nuclei next to each other. They have strong, strong, strong repulsive force. It requires super high temperature and super high pressure to make the nuclei very close. And that's what the sum is has nuclear fission, it has very high temperature. So in our case, polymer chain not going to be able to do that. So it's definitely going to be avoiding each other when it's into contact. So if we do a modification, instead of call it random walk, we can, for example, in the early days in the theory in polymer physics, people just call it self-avoiding random walk. It's again a random walk, but it will avoid itself when it's getting in close. Does it make sense? You're taking 3D random walk, but you're just going to avoid when you ever see a polymer chain has walked past that path. You're just not going to cross it again. And that turns out to be a good model to describe what is a real chain, because a real chain is avoiding itself. So it will, and here is exponent factor alpha. So you can think about in the real chain, photon chain is basically idealized chain. So you can use this to describe how much expansion you would have, because when you do self-avoiding, your chain is going to expand. So how much expand? We can describe it here. So this would be the idealized chain. So the ink need to make me keep writing. Whenever I stop, it's just not flow well. So I'll keep doing it. So this is a random walk. So if you have self-avoiding walk, you're going to have a polymer chain self-avoid walk. You have the polymer chain going to be bigger. So how much bigger it will be? And people have already measured them, and we can get what Rg proportional to. And Rg, instead of proportional to molecular weight, we can actually experimentally measure this factor. The scaling factor is 5.89, or more commonly, we just write as 0.6. Not minus, I just trying to say it's approximately 0.6. Okay? So let's first talk a little bit about easy stuff. How does this changes of exponent influence your polymer dimension? In idealized chain, it depends on n power of 0.5, right? Now we have Rg dependent on power of 0.6. How do we want to do it? Why don't we take our old friends we like to talk about is polyethylene. Let's talk about that. Joseph, I need your help. So, it's you. Let's use blue one. Hopefully this one works out better. So, let's use polyethylene as an example. let's use a million molecular weight, and let's calculate just a little bit what is the difference in size. So I think we already did it in freely joined chain model. We have RE square will equals to NL square, and I forgot what is the conclusion. How much molecular weight?
What did you say? You said 1 million?
Yeah, 1 million. We did it 1 million in the early class, right? Was that 34 nanometer or something? Anyone have taken notes? If you can help me take a look back. Probably second lecture, we actually calculate what is the dimension of 1 million polyethylene. If we don't have that, I'm happy to do it again with everyone. Is it 30 or something nanometer?
What value are we looking for again?
End-to-end distance for polyethylene molecular with a molecular weight about 1 million. That was the question I posed to everyone. If we don't have it, we can calculate. It's pretty quick.
10,960.
Say that
Is
again?
that too high? What have I written down? 10,960.
Oh, that's a contour lens, LC.
Yeah, that's right.
Oh, never mind then.
Yeah, we did calculate the N, and what did we say about end-to-end distance? Oh, no, okay, then let's do it. We have time, come on. We just need one, we first calculate N, use 1 million, divide by 28. So what's the DP? Joseph, I need your help.
1 million over 28?
Yeah, that's the DP. First we calculate DP.
Right. You have 35,000.
30. Okay, let's just take 35,000. Then we know end-to-end distance RE square will be 35,000 times 2. Remember there's 2 bonds, then times 1.54. We take a root square of first half. That will give you end-to-end distance. So can you help me take a root square of 70,000? Then times 1.54.
267, and then times 1.54 is 411.
400. Okay, let's take 400. That's good enough. So 400, it's about 40 nanometer, like I said, the 30, 40 nanometer range, right? So now how about in real chain? I'm gonna use the top space. So ignore here. So I'm gonna do RE square, depends on N. So it's gonna be 70,000 power of 0.6 times 1.54. So can you help me? This is gonna be a little bit tricky because it's not a root square. It's a power of 0.6. Yeah. It should be about 10% bigger, probably.
1,243.
Angstrom, right?
Yeah.
Okay, so I trust you. So it's 3 times bigger, roughly.
Yeah.
So you can see that's a fact of what is the idealized chain versus real chain. Real chain is just going to be bigger because for the fact that it need to self-avoid itself. And if you do a calculation, what's the difference is if you calculate this expansion factor, alpha square equals to RG square of ideal, real, sorry. This is going to be real divided by RG square of ideal. We will see this depends on N power of 0.6 B square. The bottom is N 0.5 B square. So expansion factor square will be M power of 0.1. So when your molecular weight goes up, you will have bigger and bigger discrepancy between the real chain and idealized chain. Yeah.
How did you get 70,000?
70,000 is I have my molecular weight is 1 million. My monomer molecular weight is 28. I
Oh,
divide them, then times 2 because polyethylene has 2 bonds within each repeating unit. Make sense?
Yeah.
Yeah. Did,
I think it's REE, not IEE squared, right?
yeah, IE, not IE squared. Sometimes I always, it just, we don't need the square there, okay? So, everybody understand what's the difference? And we can easily see, this would be a good example, you can tell the solvent quality. So when R depends on N is 0.6, that means your polymer is dissolving good solvents. And I can do that in this building. You just need to give me the polymer. I will be able to tell you the solvent quality. And you guys are going to probably learn more in next year in light scattering called Zin plot. Sarah, you go first.
Coming back to Amy's question, I still don't understand the 70,000 because I thought it was big N to the 0.6 power rather than little n.
Yeah,
So
but they're...
big N is 35,000.
Which part? This?
Up top,
This?
yeah,
Oh,
the 70,000.
this is proportional. So you can just write
And I thought was 35,000.
RG real chain will be REE or RG, doesn't matter. We can write RG first. N power of 1.2 B squared. Or this you can write as infinity N 1.2 L squared, etc.
Okay.
No difference. Is it still not clear?
I think maybe I just need a second. I'm having a hard time seeing that far away as well.
Okay. Why don't I write it again on the left side? That will help you.
Yeah.
Then I'll get back to you, to Amy. So all we're saying is, all I'm doing there is try to give everybody an example. What does real chain and idealized chain differs in size? So we use a polyethylene example, right? So we say what is 1 million polyethylene differs in size. So in real chain, we know end-to-end distance square will be mb squared. So in I'm getting rusty, huh? So in real chain, RE squared will be n 1.2 b squared. Or basically the same, if we remove this square term, RE will be proportional to n power of 0.6. In this case, RE will be proportional to n power of 0.5. And we can actually measure them and do it. And how do we do it in this building is, I just need to measure RG, and I just need to measure N. And I can do that if you make a polymer with different molecular weight. So I plot RG, I can use light scattering to measure it. You just need to trust me. We put the sample in the instrument, click a button, it will tell you what the RG. So if I measure 3-4 different molecular weight, and I hope you guys are learning how to control molecular weight in polymer chemistry. It's not that hard. You can control degree of polymerization through reaction times or different ratios between initiator and monomer. So assuming we can get 3 different molecular weight, and we can measure RG. So low molecular weight, high molecular weight, we can different RG, right? This makes sense? Different molecular weight, different RG. You can actually plot a log RG versus log N. Then this slope will tell you what this exponent number is. If this slope is 0.5, that means your polymer is not in good solvent. It's possible to be 0.5, right? If everybody remember when it could be, the polymer chain behave like a idealized chain? We talked about 2 scenarios it can be. Yeah, Joseph.
In a theta solvent?
Yeah, theta solvent, exactly. So it could be in theta solvent. But in most of the case, you're going to has a slope of 0.589 or 0.6. That's what 90% of polymer will behave, because when you're dissolving good solvent, it will be like that. Amy, yes?
So you had an equation on this side of the board before you erased it that had like n to an exponent over n to an exponent, and I was wondering how you got those exponents.
You have to help me memorize. Do you have it on your note?
No,
If you
I
can,
didn't get it before you erased it.
Can you elaborate one more time? Then now.
It was like this alpha equation, or it was like alpha equals like n to the.
Oh, I see. So if I use, you can directly use this.
But how did you get
So expansion factor alpha square will be RE real chain. This would be NB square, right? Real chain would be 1.2 MB square. Divided by idealized chain will be MB square. So alpha expansion factor is basically roughly equals to m power of 0.2, or you can imagine alpha will be 10% expansion factor. M power of 0.1. So it depends on n. So when the n increase, your real chain will be much bigger than idealized chain. It scales by an n power of 0.1.
I don't understand how you got the exponents of those n's though, from real values.
Let me think. How to explain the exponent? I think did you don't understand how exponent for this one? Did you understand this one?
No, I get that.
Okay, good. Then do you understand this one?
No, that's the one that is.
Okay, because we haven't explained why real chain is the exponent of 0.6. We have 2 ways to explain it. Okay, Amy? One is scientific way, and one is theoretical way. Scientific way is you can just measure it, right? I told you guys how to get this. So people actually do experimental direct measurement of polymer in good solvents. They discover that exponent is just not 0.5, it's closer to 0.6. And you can do that by making different molecular weight and measure them. It's still been done that way. So next part I'll talk to about theoretically why exponent factor is 0.6. I'll see if I can memorize that, because I haven't taught about that for a while. So, all right, I'm going to erase this. So now let's think about, so this is going to be related to what we're going to teach in rubber elasticity. And I have more discussions in another note. So when a polymer chain, now this is the theoretical part. Amy, look at here. So when we have a polymer that is compared to, I talked about this is real, and we can write an idealized chain. It will be a little bit more compact, right? Does that make sense, Amy? One is smaller, one is bigger. So this is a term that we're going to talk about more and more in chapter 7, where we talked about thermodynamics. It's about entropy. So everyone need a refreshment of what entropy is. Entropy is like state of disorder. So if you have something that is really random, that is in high entropy state. If you have something is really well ordered, that's in low entropy state. So when we think about polymer coil is, in real solvent, is expanding, it turns out that the expansion of the polymer coil will result in a loss of entropy. So when your polymer chain expands, you lose entropy. So for any polymer chain, it's always want to be in lowest energy state, which is high entropy. So the polymer coil want to shrink into this state. So it want to shrink to gain entropy. Yeah.
Did you say it loses entropy as it expands? Okay.
Yes. And we will talk much in depth in chapter 10, because when we talk about rubber elasticity, and that's exactly is when we deform the polymer coil, how much entropy we're going to gain or lose. Okay? So what is preventing it to collapse? Is polymer want to expel from each other, right? Because short range interaction between one segment chain to the other segment. Otherwise, if the chain don't like each other, it will just keep expanding without stop. But it's actually equilibrated at the real chain sizes because the contraction force is entropy force. And this can be actually discovered and measured by looking at a coil, how big the coil is. So now everybody understand what is two forces trying to battle each other? One is the polymer repulsive force trying to exclude the other chain touching itself. The other is polymer coil because it's rubber elasticity. It want to gain entropy to maintain an idealized chain. Because when you stretch more, you lose conformation. Because imagine when we talked about end-to-end distribution, we talked about that your maximum distribution is right about end-to-end mb squared. So if you expand, you just don't have a lot of conformation. Imagine it's fully extended, it's just one conformation. Every chain just stays straight, right? If it's a little bit relaxed, segment 1 and 10 can be a little bit random, other can be straight, so it has increased randomness. So these forces trying to balance each other out. And I believe I sometimes want to show an example right here. So some of my handwrites. So these are the expansion and contraction force. It's a very early theory developed by Flory. And if you haven't learned the name, he's a giant in our field. Flory-Huggins theory is based on him. So he basically says, if we consider the polymer expansion, how much energy is needed to expand depends on what the chance of your chain touching each other. If there's one touch, you can consider there's cost energy of kBT. K is Boltzmann constant, T is temperature. So kBT is usually just 1 unit energy you have at room temperature. Okay, so exclusion force is proportional to kBT times monomer units. Then how much chance you have one chain contact each other. This depends on how big the size of polymer chain. So n is degree of polymerization divided by n to n squared 3 times another chain, how long the chain. So this equation describes if I have a long chain, how much it costs energy when it's touching each other. It depends on chances of meeting another chain, number of bonds along the polymer bond. Okay? Does that make sense, everybody?
Why couldn't it be n squared? Or
Where?
Are we treating the n over r cubed as density, and that's why it's not n squared over RG?
Oh, you can rearrange it and write n squared. It's no problem. But for me, it's easy to explain what each the group means. So this means when you have a polymer chain with degree of polymerization, when you have n segments. So imagine this is the classroom. You guys each represent one of the n. So the chances of you meeting with another one student meet the student A versus B depends on what are the chances of room, how packed the room is, and how many people in the room. So if you have a lot of n, your chances of contacting will go up. And n divided by R3 is the chances of, in a given volume, meeting another student. In the polymer chain, of course, that will be meeting another segment. Right? It's n number of bonds depends on volume. Divided by volume, that will be. So how about the contraction force? This is expansion force. So the contraction force depends on this particular equation. So this is imagine your polymer chain. This is again, when we pull the polymer chain end, your entropy is high at the initial state, but once your entropy is fully stretched, it will be low. So stretched, you can think about it just like a spring. When you stretch the polymer chain end, it just want to go back. When you stretch a spring, same principle. How much forces they want to come back depends on entropy. So this entropic force, you can basically write as KB, law in possible states. This is basically chance of you finding a distribution of chain end. Maybe let me finish one thing. So your entropic spring force is kBt times radius of your polymer r times mb squared. And this is r squared mb squared is exactly the distribution of your polymer chain, because we had the same. So if you look at this equation, that means when your polymer coil extend, r increases, your force is going to go up. Your polymer chain is going to restore more. So if r is far away from mb squared, let's say we stretch it 4 times mb squared, your entropic force will be 4 times kBt, right? If this r squared is 4 times the body. So bigger you stretch, the more entropic force you have for the chain to restore. It's like Hooke's spring. So now we have C, we have contraction force, we have expansion force. We just need to add them together. When they cancel each other out, this is when your polymer will be in equilibrium and stable. So in next slide, we're going to just show you how they will behave when you have two forces battling each other.
Dr. Josh, a quick question.
Yeah. Yes.
You had S is force entropic is that proportional to that equation? So can you
This is proportional. This is S equals to KB times ln. This is omega. This means
right.
possible states of configuration. But we will revisit this more in the rubber elasticity theory. But now you just need to know that entropic force is proportional to kBt times r squared divided by mb squared.
So we can't use that equation to directly calculate the force, but it's
You can. So possible states is really the distribution of n. So that's what we talked about P, right?
Right.
So if you plug in P, that's will be exactly give you what you have in bottom.
okay.
Amy, wait. Let me. Okay, I'll let you ask. What is S?
What is S?
Entropy.
Where does it?
Come from?
No,
Yes.
I know. I was gonna ask, where does it go?
Where does it go? The entropy doesn't go.
I mean, like, is it
Oh.
relevant in the? Where does it go in the second equation?
Oh, I see. The force and entropy, I kind of skipped that step. Force and entropy are related. So if we take the partial derivative of entropy, we will get F. But that's a little bit too deep I want to cover in this class, because that's going to be in chapter 10. But I want to basically explain to you why when you have expulsion force and you have a contraction force for entropy, if we add those two forces together, when they equals to 0, we take a derivative when they equals to 0, we will be able to see how does r depends on n, because that's the radius when they are in equilibrium states. So if we use the equation we had in previous, we have v and we have r, and we add them together, takes the first derivative, and we say this segment is equal to 0. You can actually calculate r power of 5 is equals to v squared n power 3. So that's where, if we move this power of 5 to the other side, we can get radius is proportional to n power of 0.6. And that's where in real chain it's not equals to 0.5, but it's equal to 0.6. So I kind of go a long way answer your question why in real chain our end-to-end distance is proportional to n of power 0.6, power of 0.6. But hopefully this gives you some idea, because this helps you understand where the contraction force or what is expansion forces. The expansion force is coming from self-avoiding work. Then contraction force is from entropic spring effect. Okay? Amy, yeah, question.
Oh no, I'm just trying to see the equations.
Yeah, so let's use the next 5 minutes to wrap up. So we talked about, Amy, the most important part is understand what the scaling relationship. So R, G proportional to n power v. So in ideal chain, we just need to know this power factor equals to 0.5. So RG square, RG is basically n 0.5 v, right? In real chain, this v is 0.6. So your RG is proportional to power of 0.6. Proportional. Let's remove b so you can see it more clearly. And what about in Paul solvent? In bed solvent? Haha, this is something we never taught. And I want everybody to think how R depends on N a little bit. Anyone want to give a try? In bed solvent, we did one lecture talk about that. In very poor solvent, your polymer will be compact, globular, right? So in globular, say, how does the radius depends on molecular weight?
Radius goes up with molecular weight, but less fast.
Yes, less fast. How much less? So you got right. It's definitely going to be smaller than 0.5. But it will go bigger when your molecular weight go up, right? So how do we calculate it? I'll give everybody a hint. So think about the mass of sphere, how it depends on radius. If your n doubles, your basically mass doubles, your size, your weight of your compact globular doubles, right? How about r, radius? How does m, mass, depend on radius of? And we can think about intermediate volume, right? So these will be proportional. The radius volume is 3/4 of pi r cubic, right? R cubic. So in this case, volume is directly proportional to mass. Mass is directly proportional to n. So in this, we basically can reach the conclusion radius will be power of 1/3. So when your radius need to be quadrupled 3 times, 4 times, 3 times, then it will be, your RG can increase, okay? Okay, one last example. What if we have rod-like chain? How does RG depends on N? Rod-like chain. Uh-huh.
Equal to n.
Yes, it's basically RG equals to n. It's proportional n power of 1, or you can say that way. Because n goes up, your RG increases. We did the calculation in the class that RG squared equals to n squared divided by 12. So RG is directly proportional to n. Is there anything I can add? Oh, one more example. What if in theta solvent? How does RG depends on n? Of proportional?
Did you say it's the same as ideal?
Yeah, so what would it be?
0.5.
Good job. So that would be. There's one more example. I promise you, this is really the last one. I know everybody is ready for next class. You heard us so much about. How about in melt state?
Isn't that the same as the theta solvent, so it'd be 0.5?
Correct, Joseph. Good job. So that's basically, we talked a bit everything about what is the difference between the real polymer and the idealized polymer. So now reimagine what have we taught so far. I hope everything you have learned so far will help you be a little bit more confident when you see a molecular weight of polymer. You can kind of have some idea how big this thing is. Get the idea of what the RG and what the RG means, end-to-end distance means, because how these would pack in 3D make a difference. And in the next chapter, we will start talking about polymer solution. So that will be one step closer to real chain. And we're going to talk about how polymer chain will be overlapping, how they will phase separate. It's all related to what we're going to talk about. A lot of thermodynamics. Then in another month, we're going to talk about rubbers. And rubber is related to in melt states, in fully condensed state. You will learn more about these entropic spring effect, etc. Okay, so any more questions before we wrap up for chapter 7? No.
Can you re-explain how you got n to 1/3?
Oh yeah, happy to. Yes, not a problem. So this is good. So how does, in compact sphere, molecular weight depends on RG? And in compact sphere, we know that RG is directly proportional to the radius, right? Radius. We had a lecture talked about that. We calculated together how RG is related to. I believe RG squared is equal to 5/3 R squared in radius. Everybody remember that? So RG is basically, if you get the R, you can get the RG. Correct, Amy?
Sure.
Yes, sure. So now the question is, how does radius of a compact coil depends on R? How does R depends on N? That's the question. It's not clear, right? So you can understand this to be when we have a polymer with no N, we can get the mass of the polymer. How do we get the mass? M is directly proportional to N. Because the longer the polymer, you're going to increase. Does that make sense? So now imagine you have a sphere. It has a mass of M. It has a radius of R. So the mass will be density times the radius. Correct? It's just a generic relation between what the size of your sphere and what's the radius. So we know this M is directly proportional to molecular weight. And this is directly proportional to Rg. So that's where we reach N is proportional to R of power of 3. So if we move this to this side, it will be R dependence of 1/3. Okay, other questions, everybody? If no more, then my plan in the next week we can have 2 new lectures in thermodynamics, and we will have 1 lecture on homeworks, etc. Then we in that lecture on homework we can cover the first part of homework and second part of homework, and I'll post the second half homework today that you guys can take a look. It's probably it's going to be 4 or 5-ish homework questions, and we'll cover the RG and end-to-end distribution. Okay. If no more, then let's wrap up.
Do you want us to submit this homework?
Oh yeah. Send it to me. Say.
You want it in the same teams, I assume?
Yeah.